I know I look very serious. I know because I had to be serious. I cannot be like easy with somebody who is disrespecting me. I'm sorry. So guys, here is we where we stopped the last class, and probably there will be a little bit of overlap. We talked about one-way and two-way slab. So it's a slab that has some beams, and the beams they provide some support for the slab. So for this discussion here, we looked at a terminology, and this terminology called stiffness. And stiffness, it means how hard and how easy to bend things. And we said it's function of three things: the material and the cross section and the length of the member. Talking about the slab, looks like the material is the same, the cross section is the same, and then finally the length of the member will be different. And we talked about if I add some loads here in the middle of the span, the slab will simply have to take the load and then place the load into the beams. This is called load bath. So my discussion going forward called the load bath. Load bath. So when it comes to the load bath, it depends on number one, the beams. If the beams are surrounding the slab from all sides, it means the slab is supported on four sides. So that's one factor. And the other factor is the shape of the slab. The shape of the slab. So for the first example, the beam is all around, or we have beams all around the slab, and the slab is square. So the two sides or the two dimensions is simply the same. So we came up with a number, this number called rectangularity, and it's very simple. There is no sine, there is no cosine. What you do is you divide the longer dimension of the slab panel by the shorter dimension of the slab panel, and we get a number, and this number by definition, it can be 1 or anything above. It cannot be less than 1. Okay, now so for this example here, looks like we have 4 and 4, so my r is equal to 1. So what happens here, the two directions of the slab are trying to contribute and trying to carry the load. They will share 50-50. Because why 50-50? Because they are equally stiff, equally strong, equally stiff. Okay, now this discussion here applies only when we have beams all around. So the slab has support in two directions. How about if we removed beams from one direction, then the slab has only support in one direction and doesn't work by the slab shape. It works only by where is my beam. And that's happening already on the right picture here. Where are the beams? Where are the beams? So there is only one way, and this slab called one-way slab. How do we call the one on the left? Call it two-way. Why two-way? Because the load will go into two ways, X and Y, if you will. Now, going forward, what we do is, if we elongate our slab a bit, so we went from 4x4 to 4x6, and you can see my R, how much? Always the larger, which is 6, by the smaller, which is 4, so 1.5, and any number less than 2, then still work as two-way, so there is a good share between the loads. The thing is here, the shorter is the stronger. And since it is the stronger, it will carry more load. Very clear. So the shorter is 70%, for example, and 30%. And by the way, those numbers are not correct, but they give you an idea of how the load will be shared. Now, last example is, what if we keep elongating our slab? We go from 4x6 into 4x8. Find the R, so 8 divided by 4, always the larger by the smaller, so you get 2. This is the limit. Anything from 2 and above, the slab is too elongated, and one direction is so shorter compared to the other, and one direction will be stronger, way stronger than the other, and simply will say, okay, you know what, take rest, I will carry 100% of the load. It means it is one-way slab. It means 100% of the load will go into one direction, okay? So this is the concept of one-way and two-way slab. Gord?
Oh, no, it was Martin.
Did somebody?
Hi. I have a question for you if you have a second.
Is that Martin?
Yeah.
Okay, go ahead.
So when you have that factor of 2, so R equals 2 or more, you said it turns into a one-way slab. And I remember last class, if you like scrolled down a little bit where we were analyzing, there was a bunch of them. Yeah, this picture here. If those bottom slabs then are all considered as one-way slabs because there are values either 2 or 3, why would we need the extra beams in between there? You see where it says R equals 2, R equals 2. There's 2 extra beams that are vertical there. And if they're treated as a one-way slab, could we potentially treat that whole section as just one big one-way slab, or would we still have to break it up?
Okay, so part of the question, so you ask like so many questions on the same question. So I'm going to answer only one of them, and then the rest will be soon, and you will get it by yourself without me answering it. Okay. So number one, why do we have beams on this side, like here, on this side, and this side? Because they are parallel to the load, and the load simply will drop onto this beam over there and this beam over there. Correct? Why do we add those beams on the side? I
Yeah.
think this question was asked last class. I cannot remember who did ask this question, but I said for the integrity of the structure, not for carrying the load. So there are some other, for example, if I have a wind load or seismic load going into this direction here, so this beam here with the action with the column or the connection with the column, they have some resistance to this load, lateral loads. Okay, so they are not for the gravity load, but they are for other load. We call it in general structural integrity of the building. Okay, so that answered the first question. What do you think? Did you get the right answer? Does it make sense for you?
Yeah, makes sense to me. Thank you.
Okay, for the other question, can we simply think about this one as one big one-way slab? Please be patient. Your answer will be very, very shortly. Okay. Now, again, what I did last class is I skipped those 2 slides and I went to this slide and this slide and this slide and this slide here. I'm not gonna go do this business again today. But the thing is, really, guys, if you want to analyze any slab with any shape, whether we have curves or not curves, like circles and quarter circles, sometimes the architect will come up with a very creative floor plan that has some circles. There are some in downtown. There are some building which the building is circular. I think there are some condo building on the west side of downtown. They are circular, and the slab is circular, and these kind of approximate method, they don't work very well. If you encounter those kind of design, there is only one way that will give you the answer no matter what. And this is called using finite element analysis, always in industry called FE. So when you hear the word FE analysis, it means finite element. And simply how they do it without going into a very complicated discussion, they simply turn your structure into, you can see those small element, and that's why it's called finite element. Okay, and simply they apply the load, they turn the matrix into matrix. I'm not sure if you study matrix in your life, but they turn the matrix into the structure into matrix, and they solve the matrix for the deformation and the internal forces, and we're able to find all the internal forces and all the deformation. And I give you here like few snapshots. So this picture here is the deformation. This picture is in the moment in the x direction, and this moment is the moment in the y direction. Okay, this is more complicated. It's way beyond the discussion in our class. But if you continue and do university, what you will see is in university they will teach you more about finite element methods. Okay, so Tahir, how are we going to find the moments in our slab? If you give us a slab and we want to design it, you guys know, it's not a secret. If you want to design how much reinforcement that should go into the slab, you should know what is the bending moment acting on your slab. Let me see. Do you guys agree on this statement? Do you guys agree on this statement? If you want to design a
Yes,
slab,
I agree.
Your
Yes.
step is you need to find what is the moment, what is the shear, what's the axial force, what are the forces trying to play with my slab. Then I can make my slab strong enough to resist the bending moment and the shear and the axial force. So the bending moment, again, there is one universal way, whether your problem is so simple or so difficult, finite element. But sometimes if the slab plan view is simple, we can use approximate method. And that's what I'm going to teach you in my class. I'm going to teach you an approximate method that works very well when the slab is simple. When I say simple, look at my plan view. Look at my plan view. The plan view is very regular. Like it's kind of the beams are X and Y direction. There is nothing going on radial. There is no curves. There is no circle. And so we can use the method I'm going to teach you today to find the bending moments in those slabs. Now, how to do that? First of all, it's called method design strip method. Design strip method. Design strip method. And what does it mean? Strip method. It means we're gonna make some strips. Okay, strips, and those strips, like I'm already showing them on the plan view, and I will show you how to come up with these strips. Guys, listen. First of all, you need to find whether every panel, every slab panel is a one way or two ways. Again, you cannot tell. If I ask you if my slab is a one way or two ways, I think if you follow the discussion, you have to tell me, Tahir, be specific. Which slab panel? Because we have so many of them. We have one here, and we have one over there, and so on. So when we say one way or two ways, we have to be specific. Which slab panel are you referring to? Now, we've done this exercise last class, which is not very difficult. All you have to do for every slab panel is you need to divide the longer direction by the shorter direction, the length of the slab by the width of the slab. We've done this already. Look at the numbers in black. Look at the numbers in black, and you will see this is the rectangularity. Wherever the rectangularity is less than 2, then it's a two-way slab. When the R is 2 or more, it means my slab is so elongated. It means one direction is very, very small compared to the other direction, and it means there is one direction is very, very strong compared to the other direction, and it means it will absorb 100% of the load. That's not very difficult, huh? Look at my plan view and you will see I already put 50-50 or 100 or 70-30. This is the load share in each slab panel. Then what we do is, please think about this one. We're going to take a 1 meter wide design strip. Probably I need to add this on, it's over there already, it's over there. Please look at this number, 1 meter wide. 1 meter wide. Please look at my screen. I'm pointing to where I wrote the 1 meter. So 1 meter wide design strip. Okay, so the width of every one of those is 1 meter. Every one of those transparent red strip is 1 meter wide. And what we do is we say, okay, you know what? I'm going to think about this one as a beam, 1 meter, a beam that has 1 meter width, a 1 meter wide beam. One more time, a 1 meter wide beam. And please look at this, please. We know from the beam design, beams are supported on columns. I'm asking you here, this 1 meter wide beam, where are the support points? I'm going to show you where are those. Okay, so here is my first support point. Here we go. Here is the first point of support, because my design strip is supported here, and my design strip is supported over there, and my design strip is supported over there. So this design strip, or 1 meter wide beam, supported at 3 points. Okay, let's do another one. How about this design strip? Okay, so I'm going to point out to it. This design strip over here. Okay, how many support points? Okay, very simple, guys. Let's take a section through the design strip. So make a section through the design strip, and what you will see is this. Okay, please take your time. And if I want to take a section through the center line of my design strip, what do I get? I get this cross section here. Please take your time, try to match and correlate. Do I get this section here if I cut a section through this design strip? So look at this, please. So from between grid line 1 and grid line 2, it's a cantilever. Between grid line 1 and 2, it's a cantilever. You can see there are no beams over there, just like a balcony, huh? So that's a cantilever. Look at this, please. Between grid line 1 and 2, it's over there, it's a cantilever. And then at grid line 2, what do we get? We get a beam. You can see here, this is my beam on grid line 2. And on the plan view, where is the beam? The beam is over there, okay? And then between 2 and 3, there is a span. Between 2 and 3, there is a beam, like a span. And then we have another beam and support point at grid line 3, where it's over there. So my design strip is supported one more time here. And then finally, we go to another support at grid line 4, which is here. So we have a beam here and a beam here. So where is my design strip? I'm going to probably have to draw something. So this is my design strip over there. Design strip over there. Okay? And let's hatch it. So this will be my design strip. How many support points? We have support point at grid line 2, and that's the beam. And then grid line 3 and grid line 4. And we can simply convert our design strip into what we call it free body diagram. Guys, this is not new. Look at this, please. Is that shape is new? Is that the first time in your life to see this shape? What do we call it? We call it free body diagram. And it's very simple. It is kind of an abstract, huh? We abstract reality. So on the top here, that's the reality. That's the slab and the supporting beams. How about on the bottom here? That's an abstract. We're saying here that I have a support here, which is the beam, and which is this beam, huh? I have a support here and support over there, and that's it. And my design strip in blue is simply going on top of those as a continuous beam. I know I'm kind of confusing you. I'm saying slab and I'm saying beam. Because again, as I said, what we do is we think about our slab, we take some design strips, and this design strips in my slab, it will be like a 1 meter wide beam going on top of a support, which is beam on grid line number 2, number 3, and number 4. Now, guys, I'm going to zoom out and so you guys can see the correlation between the two slides. So now I'm asking you, on the cantilever, this part here, how much does it carry off the load? Does it carry 50 or 100%?
No.
On the cantilever, look at the plan view, look at my free body diagram. You can see the cantilever is a one-way slab. No choice, because there's no other way to the load to go. It cannot go to the edge of the cantilever because there is no support in here. Look at this, please. The load cannot go this way, because simply there is no beam in here. There is only one way, which is the opposite. The load 100% will go into this direction here. And that's why on the cantilever, always it's one-way slab. So 100% of the load will have to be carried by this beam. How about in between grid line 2 and 3? Please look at the plan view. In between grid line 2 and grid line number 3. What do you think? This direction here that matches and follows the design strip, does it carry 100% of the load or only 50%?
100%.
I don't know how can you say that. So the cantilever carries 100%. I'm asking between grid
50,
line number 3.
50-50.
50-50. How about between 3 and 4? 100%. Yeah. And that's exactly what's happening here. So those guys, look at this, guys. You can see the grid lines are there. Huh? Between 1 and 2, it's cantilever. So 100% has to be supported by my design strip. Between grid line 2 and 3, there is a 50-50 share. So between 2 and 3, we only apply 50% of the load. How about between 3 and 4? We apply 100% of the load. Now, guys, what happened is now you can see I'm getting close because I said, okay, you know what? Let's make a design strip here, and then I went from design strip into free body diagram. I'm asking you if this is a number, if this is, let's say WF is 10 kilo Newton per meter. If WF is 10 kilo Newton per meter, can I find moment? Can I apply the 10 here and the 5 here and the 10 here, and I can find my moment? Can we do that?
Well, to find the moment, first of all, you can have to multiply it with the, if you're only taking a strips, you have to multiply it with the tributary area, so then you can be able to get the load and multiply it by the length.
Okay. I thank you so much, Jelly, for asking a wrong question. Thank you so much. Really, really, seriously, by heart. By heart. Your question is not valid, but it's a fantastic question. Because simply, this will simply, I have to say it right now. Guys, when we design the beams, for example, when we design, let's say this beam, okay, this beam here, okay, let me ask you, what is the trip width of this beam?
100.
100 what?
There's a side of 200
No,
and
I'm asking,
that's
listen, really, you're
2000.
confused. Sorry, you're confused. I'm asking the trip width. The trip width is a meter, huh?
Yeah.
1
What is the
meter.
trip width? Who said that?
Nick.
Nick, I'll give you a couple of marks here. Nicholas.
By just saying a meter, I lose my marks.
No, but you said 100%. He said 1 meter. Your 100% is this number here. Okay? So Nick has said, okay, you know what? Listen. So Nick has said, you know what? Here is a beam. Here is another beam. Okay? And so the slab is simply throwing its load into this beam and this beam according to the arrow, which means to go to the center line, and the distance here is 2 meter. So 1 meter of load go to this beam, and 1 meter will go into this beam. Okay, that's for designing your beam. Okay, but I'm asking you, when we design a 1 meter wide design strip, this 1 meter wide design strip, what is the trip width of this design strip? Can anybody tell me?
1 meter. It says
1
still
meter.
one
Thank
meter.
you. It's over there. So you can see, the the width of the design strip is the trip width, and that's why we, for the slab, we do not multiply by the trip width, because the trip width is always 1. For the beam, we have to look at the plan view and see what's the trip width of the beam, and then we have to multiply everything that comes from the slab by the trip width. Is that clear, guys? I need to hear some noise.
Yes.
Yeah, it's clear.
Yes, that's
So
clear.
I'll say it one more time, so everybody is aware, and blame yourself. For the beam design, the beam in general does not carry 1 meter of the slab. In general, it carries more than 1 meter. And that's why every load that comes from the slab, I need to multiply by trip width. And that's why the cell weight of the beam is not included, because that's the cell weight of the beam. In our case here, we're not designing a beam, we're designing a slab. And in order for us to design a slab, we're using simplified method. And the simplified method called the design strip method, in which what we do is we take a 1 meter wide strip in my slab, and I will deal with it as if it's a beam, but it's not a beam, as if it's a beam. The difference is we're not multiplying here the load by a trip width, because always the trip width is here, is a 1 meter. Okay, anyway, there will be a numerical example where you will see this in action. Now I'm just discussing the concept, not numerical example. Now,
So, sorry, I have a quick question.
go ahead.
So when you're using that design strip, your trip width is the same width as your design strip, is what you're saying then, right?
Always 1 meter. For slab design strip, the width is always 1 meter. Okay, because I'm gonna probably, because you said that, I have to say something at this point of time. Guys, listen to me. You can take a 2-meter wide design strip. Okay? Listen, and probably it's gonna be confusing in the beginning, but it would be clear later on. You can take a 2-meter wide design strip. So in this case, everything is multiplied by 2. And when you find your moment, this moment will be acting on those 2-meter wide strip. And then when you find area of steel, you put them in those 2-meter wide strip. You can take a 4-meter wide strip. You can take a 4-meter wide strip, and you will find the load on the 4-meter wide strip, and the moment will be on the 4-meter wide strip, and the area of steel will be in those 4 meters. Here, how we do it is we get 1-meter wide design strip, and we find the load on 1-meter design strip, and we find the moment on 1-meter design strip, and then finally we find area of steel, and this area of steel we place it in 1 meter, in bare meter, bare meter. Is that clear? So everything is bare meter. That's universal agreement, by the way. But if you decide to do something like Gordon method, for example, and go for 2-meter wide strip, guess what? All your numbers will be multiplied by 2. Your moment will be twice as big. Your area of steel will be twice as big, but you will put the area of steel in those 2-meter wide. So universally, we take only 1 meter because the same, huh? It is the same. So anyway, so again, we found out so far, yes, if I'm able to convert my design strip into, think about it as a beam supported on 3 support points, and I'm able to add my loads. My question is very simple right now. If I give you this right now, and give you Safi, and give you this number is 10, and this number is 5, and this number is 10, and you have a Safi, yeah? Don't think about that you have to do it manually. If I give you a Safi, what can you do with this? You can find the bending moment that is acting on your slab, because simply the slab looks like a continuous two-span with one overhang to the left. Are you guys following?
Yeah,
I know you guys cannot do that by hand. I know that. You were never taught how to solve indeterminate structure by hand. Okay? But if you use Safi, same as we done early in this class, you should be able to find the bending moment affecting your design strip. Are you following?
yeah, we're following.
Yes,
Okay,
sir.
once we know the bending moment, what should be my next step? If I know the bending moment, and let me try to show you kind of what the bending moment will look like, huh? So the bending moment for this slab, if without numbers, I'm not gonna say numbers, but it will look something like this. So you will have a cantilever. So this is the bending moment of the cantilever, and so another curve will go from here. Probably maybe next year, not this year. Probably I need to come up with some actual diagrams from Safi or something, but not this year. Okay, guys, so what you see here, probably this will be the bending moment diagram. So what happens here on top of my beams, you get negative bending moments like this bending moment here. I'm sorry for so many arrows, but let's make it simple. Let's clean some arrows here. So guys, look at this, please. So you can see here, because I have a cantilever, so I get this negative bending moment. And then somewhere you get positive bending moment here. And then you get negative bending moment on top of your beam again. And then positive bending moment and negative bending moment. And you can see the process, because we have so many bending moments, which means I have to design more than one section. But really, as a big picture, if I'm able to convert my design strip into a free body diagram with all dimensions, and I am able to add the loads, I can use Safi to find my bending moment. And once you know the bending moment, then you can find the area of steel. Are you guys following so far?
Yep.
Yes, sir.
Still following.
Excellent. Now, okay, excellent. So look at this, please. So now I know this is kind of a time consuming to do that, but just please follow the discussion, huh? I'm not asking you to do anything by yourself for now. Now, do you think if I use this design strip, I can simply, if I am able to find bending moment and I'm able to design, you know what? I can simply place my rebar in this direction. So I'm going to have a rebar here that covers the cantilever, and I have here some rebar in the middle and another rebar on top of the beam, same as we've done with the continuous beam from 2 classes ago. Continuous beam, we know how to add the reinforcement in a continuous beam. But did I finish the beam design, the slab design? I already finished one, huh? And you can see I can apply, because look at this. What happens to the next meter? Let me ask you, what happens to this meter? There is a copy and paste, like a adjacent 1 meter right and left of this design strip. Do I have to analyze it one more time? Or whatever I did for this meter, I can apply it all the way to the end? What do you
You
think?
can apply it to
You
the
can
end.
apply
It
to
is
the end.
identical. Those are twins. Huh? Look at every one of those design strip. They are identical, which means when I finish the design of the design of this design strip, it means I can simply apply the design across. Across from where to where? I'm going to show you what dimension line is going to be from this to this. Okay? So same, because again, they are identical, 100% identical, with the same load, with the same support system, so with the same span. So there is no change. So the moment will be the same, and the area of steel will be the same. But I'm asking you, if I put, like, let's say 1 hour and I'm able to do SAFI and I'm able to design all the sections, am I done with the plan view design? I have here a floor plan, huh? A floor plan. Am I done? Is it one design strip sufficient to cover the entire area, or I need more design strips?
I think you need more.
Excuse me?
More?
Okay, great. Thank you so much for this answer. Let me show you what is next. Okay, let me clean things up and then let me show you next. So guys, you can see here is my first design strip. It's over there. This is design strip number 1, which I gave you kind of details on how we analyze it. Okay, but finishing design strip number 1 was not covered, and I'll tell you the reason. Anytime you see an arrow with load path and is not covered by design strip, you're not done yet. I'll say it one more time. Anytime you see an arrow that shows the load path and it's not covered by design strip, what happened is you haven't secured this load path. Which means what? Which means, look at this. Do I have a design strip for this arrow here? Now? Now I don't, which means I'm not done yet. So what to do is you simply have to simply put this design strip. So this design strip here, it will simply cover this arrow here, and we will find moment and we will place our rebar on this direction here. Are we done if we have two? So we have two. So far, we have two. Are we done? Not yet. Why is that? Because look at this arrow here. This arrow here is not covered, and the rest are not covered. So what should I do? I should have here another design strip. And this design strip will simply secure a load path for this load, the 100% in the middle. Okay? Now, what else? On this side here, I need one design strip that covers the 170%. And this design strip here will be continuous two spans. Okay? And then finally, I need a design strip here to cover the 30% of the load that works as a simply supported between this beam and this beam. So the idea is, guys, every time you see load path, you must secure it by a design strip. A design strip. The design strip, sometimes it can be simple and sometimes it can be continuous. In this example here, for example, let me ask you guys, this design strip here, can you talk about the statical system or structural system? Is it simply supported as a cantilever or is a continuous beam? Any help? This design strip over there, I'm pointing to my design strip right now. Is it cantilever, or simply supported, or continuous?
Continuous.
It's continuous. How many spans, sir?
3.
Where
2
is the
spans.
three?
3 beams, sorry. 3 columns, 2 spans.
2 spans, huh? So this one span and this another span here. Remember, where are the support point? My design strip is supported here. So that's one support point on a beam. And my design strip is supported here. And then finally, my design strip is supported here. So we have 3 support point and we have 2 spans. And that's why this design strip is a continuous 2 spans. Now, let me ask you, how about this one here? Is it continuous 2 spans or 1 span? What's going on there? What do you think?
1 span.
One span.
Why is that? Because
One
it's
span.
1 span, and please don't be deceived, huh? Because this is open. There's no slab in here. So my slab is not continuous. It ends here. So this is, we have 2 support point, 1 support point here, another support point here. So this design strip is simply supported between the 2 beams. Guys, here is the big picture. The big picture is, number 1, you have to look at every individual slab panel. Say whether my slab panel is 1 way or 2 ways. Depends on, do I have beams all around? Number 2, depends on the shape of the slab. Okay, now I know. So I put all these arrows in red and blue, and I say 50, 50, 100, 170, 30. Once you do that, next step is we place design strip. In general, one design strip is not sufficient. In general, sometimes yes, it's one sufficient, but sometimes in general it's not sufficient. And this example tells you we sometimes need more than one design strip. How do I know the number? What happens is, make sure that every arrow that has a load, you have secured by a design strip. Please look at my plan view right now. There is not a single arrow that is not covered by a design strip, which means how many design strips I have. I have total of 5 design strip. 5, please count them. We have total of 5 design strip. Some of them, they are simply supported. Some of them, they are continuous 2 spans, and some of them, they are continuous 2 spans with overhang cantilever, same as design strip number 1. Are you guys following?
Yep.
Yes.
Yes, sir.
Excellent. So let's take a break. I will see you guys here sharp at 2. Thanks.